it's a pleasure to welcome, well, I know him as Alex Falk. I'm not sure I'll pronounce his Chinese name right, but Chi Kwong, is it Falk?
Yeah.
All right. And he's from New York University in Shanghai. And today he's going to talk about Equvariant twisted KK theory of non-compact Lie groups. Over to you.
Okay, thanks, Matai. First of all, I would like to thank the organizer for inviting me to speak in this global non-commutative geometry seminar. So today I would like to talk about a joint work. Sorry, oops, just a second. So I want to turn the page. No, sorry. Oh, okay, it works. So today I would like to talk about the joint work with Matai Varghese, which was recently published in CMP. This work is about the twisted equivariant KK theory for non-compact Lie groups. This work, on the one hand, was inspired by the famous result by the Fried-Hopkins-Telemann theorem, which gives a canonical link between the equivariant twisted K theory of a compact Lie group and the representation theory of its loop group. On the other hand, this work is also inspired by Meirenken's work on the geometric quantization of the Quasi-Hamiltonian manifolds. So I will spend the first part of this talk on reviewing these two results by Fried-Hopkins-Telemann and Meirenken. And after that, I will present our generalization to the non-compact setting by giving a suitable formulation of the equivariant twisted K theory of the non-compact Lie groups in terms of the equivariant twisted correspondences in KK theory. And next, we will discuss the Bum-Kohn and Kohn-Kasparov maps for the non-compact Lie groups with the twist. And then, based on this, I will present conjectures related to the representations of the loop group of non-compact Lie groups. Okay. So throughout this talk, for simplicity, I will just assume that K is a connected, simple, and simply connected compact Lie group. And I view K as a K-space by the conjugation action on itself. So the twist for equivariant K theory, which is also the local coefficient for K theory in the algebraic topological language, is classified by the equivariant third cohomology. If the space is the compact Lie group K, then this equivariant third integral cohomology is isomorphic to the ring of integers. So this equivariant third cohomology also classifies the central extension of the loop group LK by the circle group U1. So I'll let tau KK be a twist on K corresponding to an integer small k. So we can realize this K as a Dixmeyer-Dowdy bundle, which is a fiber bundle with fiber being the space of compact operators. So for the compact Lie group K, such a Dixmeyer-Dowdy bundle can be constructed using the so-called based path group construction. So here, I'll let this PEK be the based path group and LEK be the based loop group based at the identity element. And this script H sub K is the basic representation of the level 1 central extension of the loop group LK. And this Dixmuir-Doughty bundle is basically the product of base path group PK and the space of compact operators of the K tensor power of script H sub K, mod out the action by the base loop group LEK. And then we define the level L positive energy representation of the loop group, which is the kind of representation we care about, to be the representation of the level L central extension, where the loop rotation adds with the positive weights. Oops. Okay, so here's the statement of the Fried-Hopkins-Telemann theorem, and I divided into two parts. And well, this is just the one version of the Fried-Hopkins-Telemann theorem for the simply connected compact Lie groups. So Fried-Hopkins-Telemann also get their theorem for the most general compact Lie group case. So here I just state the the theorem in the special case. So first we have that the equivariant K theory of K is a ring, with the ring structure being the Pontryagin product induced by the multiplication map of K. And then we'll let H check be the dual Cossiter number of K, and K is greater than or equal to H check. Then we have this push forward map from the representation ring of K to the twisted K theory of K, induced by the inclusion of the identity element into the group K. So it turns out that this push forward map iota is onto, and the kernel of this push forward map is precisely the level, the so-called level K minus H check Bernoulli ideal of the representation ring RK. So it is known that the quotient of RK by the Bernoulli ideal is isomorphic to the so-called Bernoulli algebra, which is the representation group of the positive energy representation of LK equipped with the intricately defined product structure called the fusion product, which traditionally are defined using the conformal field theory and the studies of the moduli spaces over Riemann surfaces. So I'm not going into details about the definition of the fusion product. So basically, this part of the theorem says that the equivariant K theory, the equivariant twisted K theory of K is isomorphic to the Bernoulli algebra. And through this isomorphism, we give the interpretation of the fusion product in terms of the algebraic topology of the twisted equivariant K theory of K using the Pontryagin product. And here you may have observed that, that there is a shift of level by the H check, the dual Cossiter number. So that is because this dual Cossiter number is precisely the level of the spin representation of the loop group LK, which appears in the Dirac induction construction of the positive energy representation of the loop group LK. Okay. So just like the representation of the compact Lie group K, there is a nice classification of the irreducible positive energy representation of LK using the highest weight. So it turns out that the irreducible positive energy representations of LK are in one-one correspondence with their highest weight, which are in the set of level K minus H check weight. So these are the weights lying inside the level K minus H check Weyl alcove, which is the part of the positive Weyl chamber, limited by this inequality here. So here B is the basic inner product defined on the dual of the Lie algebra, and alpha max is the highest root. So note that the push forward of the irreducible representation V mu of the compact Lie group K turns out to be the irreducible positive energy representation of LK with the highest weight mu, and I denoted by W sub mu. So here's an easy example. So we take K to be SU2, then the dual constant number is 2. So in general, the dual constant number of SUN is n. And then according to Fried-Hopkins-Telemann theorem, the equivariant twisted K theory of K is isomorphic to the level K minus 2 Bernoulli algebra, LK, which to be more precise is the quotient ring of the representation ring of SU2 generated by its standard representation by the Bernoulli ideal generated by the K minus first symmetric power of the standard representation. As an abelian group, the Bernoulli algebra is generated by K minus 1 irreducible positive energy representations, and each of which is labeled by the level K minus 2 weight of SU2. Okay. So actually we can also describe the equivariant twisted K theory using a geometric model of a K homology. So if we generalize the work by Bailing Wang, who gave the geometric model of the non-equivariant twisted K homology, and the work by Baum, Oyono, Schick, Water, who gave the geometric model of the equivariant non-twisted K homology, we can give the geometric model of the equivariant twisted K homology of a space X, which is oriented compact K manifold. So basically we can define the geometric model of this equivariant twisted K homology using the geometric cycles consisting of the data M, F, and E, where M is a K manifold, and F is a map from M to X. So it is a K equivariant map, and E is a complex K vector bundle over M. And we require that M be satisfying this so-called twisted spin C condition, which says that the tensor product of the pullback of the twist tau to M and the Clifford bundle of M can be Morita trivialized by some K vector bundle S. So in mathematical physics, this twisted spin C condition is also called an Fried-Witten anomaly cancellation. We subject these geometric cycles to the three relations, namely the K equivariant cobordism and disjoint union of geometric cycles corresponding to the direct sum of them. And lastly, the so-called bundle modification, which amounts to the equivariant Bott periodicity. Rankin showed that the equivariant twisted K homology of K, which is isomorphic to the equivariant twisted K theory of K through Poincare duality, is generated by the geometric cycles corresponding to some special kind of conjugacy classes, which he called the quantizable conjugacy classes. So these conjugacy class contains the special element, the exponential of this element here. So the B sharp is the map from the dual of Lie algebra to G induced by the basic inner product. And the map involved in the geometric cycle is simply the inclusion of the conjugacy class into the group K. So it turns out that these quantizable conjugacy classes are special examples of the so-called quasi-Hamiltonian manifolds defined by the Alessi-Malkin-Rankin. So we can view the quasi-Hamiltonian manifolds as a generalization to the ordinary Hamiltonian manifolds, which is equipped with a moment map taking value in the view of the Lie algebra. So for the quasi-Hamiltonian manifolds, they are equipped with instead the so-called group valued moment map, taking value in a group which acts on them. So to be more precise, the K manifold N is quasi-Hamiltonian manifold, or a Q-Hamiltonian manifold for short. If there exists a K invariant two form on N and an equivariant K-valued map mu N, the so-called group valued moment map, satisfying three conditions. So the first condition says that the D of this K invariant two form plus the pullback of the Cartan three form on K is 0. So later on, we'll see that actually this first condition is related to the twisted spin C condition. And the second condition is a generalization of the Hamiltonian equation. And the third condition is the minimal non-degeneracy of the two form omega. So we allow some sort of a, actually I mean the minimal degeneracy of omega. So we allow certain degeneracy of omega for the quasi-Hamiltonian manifolds, unlike the non-degeneracy of the symplectic form of the ordinary Hamiltonian manifold. So you may think of the quasi-Hamiltonian manifolds as the exponentiated version of the ordinary Hamiltonian manifolds. Actually, one can construct a quasi-Hamiltonian manifolds from the ordinary one by exponentiating the ordinary moment map. So a prototypical example of the quasi-Hamiltonian manifolds, as I have said, is the conjugacy class of K with the moment map being the inclusion. So you can think of the conjugacy class as the exponentiated version of the co-adjoint orbit of the Lie group, which is well known to be a Hamiltonian manifold. So Rankin showed that any quasi-Hamiltonian manifold has a canonical twisted spin C structure in the sense that there is a spinor bundle S which Morita trivializes the tensor product of the Clipper bundle of N and the pullback of the H-check tensor power of the X-Mir-Dowdy bundle classified by the Cartan 3 form eta K. And we say this manifold N to be quantizable at level K minus H check if there exists another vector bundle E over N such that it Morita trivializes the pullback of the K minus H check tensor power of the DD bundle classified by the Catan3 form. So if you do the tensor product of these two isomorphisms, so namely this isomorphism, so namely this isomorphism and this isomorphism, then you get the required twisted spin C condition in order for the geometric cycle involving N to be really a geometric cycle. So Myron can define the geometric quantization of the Quasi-Hamiltonian manifold to be this triple N and the moment map mu N and the tangent bundle Tn. And this is an element in the twisted K homology of K. So now let's turn to the non-compact case. And as before, for simplicity, I'll assume that G to be connected, simply connected, simple, non-compact, and linear Lie group. And K is assumed to be its maximal compact subgroup. So now the question is, how should we formulate the equivariant twisted K theory of G? So the first order of business is to define the Dixmuir-Doughty bundle realizing the twist. Or in the very first place, how can we classify the twist on G? So it turns out that the twist of G can also be classified by the equivariant third cohomology of G, which is isomorphic to the integers. I'll let tau GG be the twist corresponding to K, the integer K. So again, we can realize such a twist by the Dixmuir-Doughty bundle constructed using this base path group construction. So here, this script H sub Q is the basic representation of the level 1 central extension of the loop group of Q, which is a maximal compact subgroup of the complexification of G. So this script H sub Q is a representation of LQ. And we know that such a representation can be extended holomorphically to its complexification, which is LGC. And we can further restrict this representation to the base loop group LEG. And in this way, this base path group construction makes sense. So now the next question is the formulation of the twisted K theory of G. But we observe that due to the non-compactness of G, the conjugation action of G on itself is not proper. So it doesn't make sense to simply talk about the equivariant K theory of G. To get around this, instead we consider the KK theory of G over K and C star algebra of the space of sections of tau GG vanishing at infinity. So it turns out that the equivariant twisted K homology of K is naturally isomorphic to the KK theory. So it is not hard to realize this isomorphism. So basically, this isomorphism is given by a composition of the equivariant Poincare duality isomorphism, sending the K homology to the K theory, and the Thom isomorphism, which is the map induced by the inclusion of K into G. So such an induced map can be regarded as a Thom isomorphism because G is equivariantly diffeomorphic to the product of K and G over K, which is diffeomorphic to an Euclidean space. And so G can be regarded as a K vector bundle over K. And another constituent map in this isomorphism is the Green-Joke isomorphism, which is the isomorphism between the equivariant K theory with the K acting and the K theory of the cross product C-star algebra with K acting. And finally, we also have this constituent map, which is the restriction map, restricting the G action to the K action. So all these constituent maps are isomorphisms, and so is the composition. So now we have the description for the equivariant twisted K theory for the non-compact Lie group G. And the next question is, what are the generators of this KK theory? So it turns out that we can also give a geometric model for the KK theory of the two spaces X and Y by generalizing the work by Baling Wang and the work by Skandalis, who gave the description of the geometric KK theory using correspondences. So now we first define the G equivariant twisted correspondence between the G space X and another G space Y with a twist on it, tau Y, to be this diagram. So on top of the diagram is the tuple M and E, where M is a G space and E is a G vector bundle. So this diagram also consists of two maps from M to the two spaces X and Y respectively. So we have this backward map B, which is a proper G map from M to X. And then another G map, the forward map F from M to Y. Not necessarily proper, but we require that F satisfies this twisted spin-C condition. Okay, so pullback of the twist along F tensor with the Clifford bundle of M can be Morita trivialized by some G vector bundle S. So this is a definition of the equivariant twisted correspondence. And we will use this definition to construct the geometric model for the equivariant twisted KK theory. Actually, the construction is analogous to the previous construction of the geometric model of the K homology. So we define the geometric model to be the group generated by the isomorphism classes of G equivariant twisted correspondences, subject to the same three relations as before, namely the G equivariant cobordism, disjoint union corresponding to the direct sum and the bundle modification implementing the Bott periodicity. So in more details, we can construct the isomorphism going from the geometric model to the analytic model of the KK theory. So this isomorphism phi sends the equivariant twisted correspondence on the previous page to the intersection product of the three KK elements related to the data of the correspondence. So here, the double bracket E is this KK element of the KK theory of the two identical C-star algebra, space of sections of Clifford bundle of M. And this is related to the vector bundle E. The B upper star is the KK element induced by the pullback map B upper star going from the space of sections of the Clifford bundle of X to the space of sections of Clifford bundle of M. And this F shriek obviously is the KK element induced by the forward map directly. Okay, so this is the geometric model. And now, oops. So now we can describe the KK theory of the non-compact Lie group G using this geometric model. So first, note that G over K is spin C due to our assumption that K is simply connected. And so this C-star algebra of the space of sections of the Clifford bundle of G over K is Morita equivalent to the C-star algebra of space of continuous functions of G over K vanishing at infinity. And so we have this isomorphism of the KK theory. And turns out that this KK theory for the non-compact Lie groups is freely generated by the correspondences constructed from the quantizable conjugacy classes in K. So here in the top, the space D mu is a fiber bundle over G over K, with the fiber being the quantizable conjugacy class script C mu. And the E mu is the vertical tangent bundle of the D mu. And the backward map is the natural projection from the fiber bundle D mu onto the base G over K. And the forward map is given by this conjugation. Okay, so it sends the equivalence class of G comma C to conjugation of C by G. All right, so this is our description of the equivariant twisted KK theory of G in terms of the geometric model of the correspondences. And we can also use the correspondences to describe the geometric quantization of the quasi-Hamiltonian manifolds. So in order to do this, we need to make some technical assumptions. So first, we define a strongly stable element of G. So we say G is a strongly stable element if its centralizer is compact. And we let the script U be the set of strongly stable elements in G. So it turns out that the set U is open and it is non-empty if and only if the rank of G and K are the same. So in the case the set U is non-empty, then we can describe the set as the set of all the conjugates of the regular element in the compact maximal torus T of the Lie group G. And then we have this result, which basically says that, that there is a correspondence between the quasi-Hamiltonian manifolds with a compact Lie group action, and the quasi-Hamiltonian manifolds with a non-compact Lie group action. And this correspondence is realized by the induction. So now we assume that G and K have the same rank, and M is a quasi-Hamiltonian manifold with a proper G action. And we further assume that the image of the moment map of M lies inside the set U. And we suppose that the composition of the moment map with the natural projection from G to G over K has the identity coset EK as a regular value. And in assuming so, we can ensure that the preimage of K under the moment map mu M is a manifold, which I denote by N. And under this assumption, we have that the manifold N with the restricted group action K and the restricted 2 form and the restricted moment map is a quasi-Hamiltonian K manifold. And also M is G equivariantly diffeomorphic to a fiber bundle over G over K with the fiber being N. And the moment map on M is given by the adjoint action of the moment map on N. Okay. So it is in this sense that the manifold M is an induction of the manifold N. So with this, we can now define the geometric quantization of the quasi-Hamiltonian manifold as an equivariant twisted correspondence. So suppose we have a quasi-Hamiltonian manifold satisfying the quantizability condition and the conditions of the theorem on the previous page. Then we can define the equivariant. So we can define the quantization to be the equivariant twisted correspondence, where at the top of this correspondence is the tuple M and vertical tangent bundle G times Tn over K, and backward map is the natural projection from M to G over K, and the forward map is given precisely by the moment map. Okay, so next we will turn to the discussion of the Bum-Con and Con-Kasparov maps for the non-compact Lie group G. So previously, we considered the KK theory of G, and now we can as well consider the K theory of the cross-product C-star algebra of space of sections of tau GG vanishing at infinity. And also we consider this square diagram. So the top map of the square diagram is the Con-Kasparov map, which sends the representation of K through the Dirac induction to the index of the Dirac operators over G over K twisted by that representation of K. And the left vertical map is just this push forward map induced by the inclusion of the identity. And the right vertical map is sort of analogous to this push forward map induced by the inclusion of the identity. To be more precise, it is defined using the intersection product of some KK elements, and among them the Dirac element and the dual Dirac element, and also the Kasparov descent map. So I'm not going into the precise definition of this right vertical map, but you can think of it as the analog of the left vertical map. So the bottom map Q is the composition of the four maps here. So the first map is the intersection product with the Dirac element, which is the fundamental class of G over K. The second map is the intersection product of the KK element I induced by the inclusion map of K into G. So the first two maps can be regarded as the Thom isomorphisms. And then the third map is the inverse of the restriction map, restricting the G action to the K action. So the first three maps are known to be isomorphism. And then the last map is the Bum-Con map, which we will show that is an isomorphism.
May I say, before you move on?
Yes.
The top diagram, the horizontal arrow. I mean,
oh, yes.
It in an essential fact that due to the work of many people, including Chabad, Echterhoff, and Nest, is that that's an isomorphism. Because the K theory of C star G is not a ring in a natural way, okay? So
right.
we use the fact that it's an isomorphism to transport the ring structure. We use that in an essential way in our work, okay? So you will see that. So you just point it out, please.
Yes, yeah, actually, yeah, I will point out the relevance of the work by Chabad, Echterhoff, Nest later on. So, and then the concast prof map can be realized as the composition, the map Q with the two more maps. So the first map being the Green-Juke isomorphism, and the middle map is simply the inverse of the Thom isomorphism. So one of the main results in our paper is the following theorem. So first, the square diagram commutes. And second, the Bum-Con map is an isomorphism. And so is the bottom map Q. And also the concast map is an isomorphism. So I'm going to give you a sketch of proof of Bum-Con map is an isomorphism. So the proof of the fact that the concast map is an isomorphism is entirely analogous to the Bum-Con map. So the idea is to use Majority sequence for the K-theory groups with respect to a special kind of finite G invariant closed cover of G. And we require this closed cover to satisfy that the Bum-Con map restricted to any closed set in the closed cover, and any intersection of them is an isomorphism. And we find some suitable sufficient conditions for this closed cover satisfying this condition. We assume that the closed set in the closed cover and their intersections are stratifications of finitely many strata, OJ. And we assume that each stratum falls under two categories. So the first category is a finite disjoint union of fiber bundles over some cones on which G acts trivially. So here by cones, I mean a space whose one-point compactification is contractible. So the second category is a finite disjoint union of conjugacy classes. So we will verify the Bum-Con map, the isomorphism of Bum-Con map for each of these two categories. So for the first category, the Bum-Con isomorphism holds trivially. That is because all the K groups involved vanish. So we can use a very easy short exact sequence argument applied to the C-star algebra of the cones and the C-star algebra over a point to show that all the relevant K groups vanish. Okay, so this is pretty simple. So as to the second category, we'll verify the isomorphism of the Bum-Con map using this commutative diagram. So let's say I have this conjugacy class script C, and we have an element G inside this conjugacy class, whose stabilizer subgroup is H. And in this way, the conjugacy class is diffeomorphic to G over H. So in this commutative diagram, the top map is just the Bum-Con map restricted on the conjugacy class. And the two vertical maps are isomorphisms because they are actually the induction map from H to G. So to show that the top map, which is the Bum-Con map restricted onto the conjugacy class, it all boils down to showing that the bottom map is an isomorphism, but the bottom map is simply the Bum-Con map for the H action with the coefficient KH, a space of compact operators on the Hilbert space H. And it is known that such a Bum-Con map with coefficient is an isomorphism by the work of Chabot, Ashtaroth, Nest. So we can actually explicitly construct the closed cover using this so-called Steinberg map, which sends a group element G to the group characters of it corresponding to the fundamental representations of the complexification of G. So by definition, this Steinberg map is conjugation invariant, and each fiber is actually a stratification of conjugacy classes. So if you take G to be the special linear group, you can see that each fiber is a stratification of conjugacy classes labeled by the Jordan block. And the base, which is the image of the Steinberg map, can also be stratified according to the so-called genericity. So again, if you take G to be the special linear group, the genericity has something to do with the multiplicity of the eigenvalues of G. So the more generic the stratum is, the lower the multiplicity of the eigenvalues of G is. So it turns out that the strata in the image of the Steinberg map are the so-called real semi-algebraic set. Using some results from the real algebraic geometry, we can see that this stratum can be finitely triangulated. And so we can do finite triangulation of these strata in the image of the Steinberg map to a finer triangulation in such a way that the unbounded simplex in the triangulation corresponds to a cone, and the bounded simplex in the triangulation corresponds to a compact simplex. And in this way, we can get our desired closed cover. And that gives the proof. Okay. Oops, sorry. And finally, based on this discussion about the BOM-CON and CON-Kasparov map, I would like to present some conjectures about the representations of loop group LG. So recall that the CON-Kasparov map is realized by the Dirac induction. And the K-theory of the reduced C-star algebra of G gives you the so-called tempered representations of G. So these are the representations of G whose matrix coefficients are well behaved. So they account for the positive Plancherel measure in the decomposition of the regular representation of G. So in particular, if G and K are of the same rank, then this K-theory group gives you the discrete series representations and their limits. So any irreducible tempered representation of G can be constructed by means of the parabolic induction. So it can be constructed from the induction of a representation of the so-called cuspidal parabolic subgroup P, which by the Leibniz decomposition can be realized as the product of three groups MAN. And the representation actually is associated with a discrete series representation or the limit of discrete series representation of the group capital M. So again, we have this commutative diagram, and inspired from this commutative diagram, we have these two conjectures. Okay. So we conjecture that the K group, the K theory of the cross product C-star algebra of sections of tau GG gives you the tempered representations of the loop group LG in a suitable sense. And we expect that these tempered representations can be constructed also by the parabolic induction in some way. And then we also conjecture that the bottom map Q is analogous to the top map, the CON-Kasparov map. So the top map Q is given by the Dirac induction, which sends the positive energy representation of K with highest weight mu to the index of the Dirac operator over this infinite dimensional homogeneous space LG over K, twisted by the representation of K with highest weight mu. Okay. So here's the example. In the case where G is a complex simple Lie group, so let beta mu be the K-theory element associated with the unitary principal series representation of G induced from a discrete series or the limit of discrete series representation of M with the weight mu. So if we input the specific representation to the previous commutative diagram, then we will get this commutative diagram on this page. So that the top map, which is the CON-Kasparov map, sends V mu, the irreducible representation of K, to this unitary principal series representation associated with the weight mu plus rho. So this is the result due to Pennington-Plymouth in the case where G is a complex simple Lie group. And well, according to our conjecture, we will expect that in the lower right corner of this commutative diagram, we should get a representation, probably some principal series representation of the loop group associated with the weight mu plus rho. And according to the commutative diagram, we have that the K theory of the cross product C star algebra of the twist is an abelian group freely generated by the set of K minus H check weight shifted by the rho. So this is the isomorphism we get. Oops, sorry. So this is the isomorphism we get from the commutative diagram. Okay, so I think I should stop there. Thank you for listening.
Okay. Any questions? So we are open to questions, which Alex will answer.
Okay, so maybe I have a question which is not so related to the main topic. Actually, in the early part of your talk, you mentioned that so part of what you did with Matai is a twisted version of what Bailing Wang and
yes,
the Baum and company did. So
right.
their approach is here. Yes, on this page. So their approaches are they equivalent? Or I mean,
so we basically combine the results to get our geometric model for the twisted KK theory. And,
this part I think I understood. What I would like to ask you is that the approach of Baum, Schick, etc., and the approach of Bailing Wang, these two approaches, are they kind of there's kind of equivalence in their steps, or
I think so while I don't know about the very deep.
No, the paper of Wang actually describes K homology, right?
Yes.
Of a compact space, no groups.
Okay.
And the same with with Baum and Schick and Walter, they do a compact group on a compact.
On compact group, yes. Okay.
Yeah.
So yeah,
that's the main difference, but they actually do a lot more. They show that it's actually a homology theory. So Bailing didn't prove that it was a homology theory.
Okay. Thank you.
There are various, many authors have contributed, so I must say. So all we did was in the non-compact case, but it was essential for us to use the non-compact.
Yeah, sure. Okay. I see.
So let me.
Thank you.
Sorry, let me add that Wang's paper makes a lot of use of the cobordism theory, which I don't think is found in the work by Baum, Onyono, Schick, Walter.
Yeah,
So
yeah.
I think that their emphasis are a little bit different.
Yeah, sure, of course. I mean, for Paul Bohm, I think this vector bundle modification is something that he very dear to him.
No, they had to use spectra in
They had to use spectra. Okay.
Homology. So
Yeah.
of course, Biling didn't, but you need a spectra in order to show its homology theory. Okay, so it's a very algebraic topological paper.
Yeah. I see.
Right.
Thank you.
Any other questions? I don't see anything in the chat, so.
Yes. Yeah.
So if not, let's thank Alex again
Yeah.
for nice talk.
Yeah. Wonderful talk.
Thank you.
Okay, I will stop recording.